Motion in central force field, the problems related to this very important chapter we have discussed in very detail in my earlier videos. The last concept of the motion in central force field we are going to see now, and this is related to a very important problem of artificial satellites. Actually, you know that the motion of a planet and its orbit around the sun is actually along an elliptical orbit. You have studied Kepler's laws of planetary motion. The first law says that all planets revolve around the sun along an elliptical orbit, and the sun is situated at one of the foci of the ellipse. Okay, actually, this theory, which we have already discussed earlier for the orbits and the planetary motion, are valid for the discussion of satellites too. So first of all, we will see here what is a satellite and what when you say artificial satellite, what does it mean? Okay, this is a very simple concept. Actually, in geography, you have studied that any heavenly body which revolves around the sun is called planet, and a heavenly body revolving around a planet is called a satellite. In geography, in fact, there is a remarkable difference between a satellite and a planet. But in physics, when we study actually astrophysics, we do not differentiate between a planet and a satellite. Okay? Because here the term satellite is used both for the satellite and the planet in same meaning. Because in physics, or particularly in astrophysics or astronomy, we simply say that any body which revolves constantly round a comparatively larger body, it means a body of larger mass, that is called a satellite. For example, you can say that, as you know, the earth revolves round the sun and the moon revolves round the earth. You know it. So in this condition, you can say, since earth is revolving around the sun, so earth is a satellite of the sun. Although in geography we say that earth is a planet, but here planet is not different from satellite, because in accordance with the definition of a satellite, any body which revolves a relatively a massive body is called a satellite. So since earth is revolving around the sun, so in this sense we can say that earth is a satellite of the sun. And on the other hand, since moon revolves around the earth and earth is very massive in comparison to the moon, so you can say that moon is a satellite of the earth. Okay, so here all planets can be treated like a satellite revolving around the sun, and all the moons which revolve around the different planets like earth, like Jupiter, like Saturn, all those are called actually satellites. Okay, so you can say in the broad sense, a body which revolves around a relatively larger massive body, that is called a satellite. Okay, now here I have given two examples, that earth is a satellite of the sun and moon is a satellite of the earth. Okay, and you know that the earth and the moon are not man-made objects. These are actually natural objects. So we simply say that the satellites which are not man-made, but if their existence is naturally, that is called natural satellites. So Earth and the Moon are examples of natural satellites. Okay. Now here, whenever a satellite revolves around a massive body, then what's the reason behind the revolution? Actually, the satellite experiences gravitational force due to the massive body, and that force actually provides the necessary centripetal force for its revolution. Okay, and that gravitational force is actually found by using the Newton's law of gravitation. So I have mentioned it here that each one of these satellites is attracted by its primary. Primary means here in case of Earth, this is the primary is Sun, and in case of Moon, the primary is Earth. So due to the attraction of the Sun, the Earth revolves around it, and due to the gravitational attraction of the Earth, the Moon revolves around it. And that gravitational force is simply found by using the universal law of gravitation proposed by Newton. Okay. So as Earth and Moon, which I have given as an example, are not man-made, but they are actually natural objects. So I have told you that these are natural satellites. But scientists have also been able to place man-made satellites revolving around the Earth and also around the Sun. But our present interest is the satellites revolving around the Earth. But that satellite may revolve around the Sun too. Scientists have developed so many satellites. There is each and every developed country and developing country has a satellite launching program, and so many satellites have been launched till date. Okay. So when you think about an object which is man-made and that are set up in a particular stable orbit, and that object revolves around the Earth or the Sun, that is called an artificial satellite. Okay. So in one sentence you can say that the man-made satellites are called artificial satellites. Okay. So I have mentioned it here. You can see that scientists have also been able to place man-made satellites revolving the Earth and also the Sun, and these are called artificial satellites. Okay. Now as I have told you that for dealing with the motion of these artificial satellites, we can use the theory developed in general for the motion of planetary motion of the different planets around the Sun, which are governed by Kepler's laws of planetary motion. Actually here our prime aim regarding this artificial satellite is to find the speed with which it revolves in the orbit, and what will be the time period, that is the period of revolution or time taken by the satellite in completing one revolution around the massive body or around the Earth or Sun. Our prime aim is to find that. Okay. So now you can see that if you talk about an artificial satellite of the Earth which is placed in a stable orbit that will revolve around the Earth, and that satellite is actually set up in the orbit by the use of or by the help of multi-stage rocket. Multi-stage rocket is utilized to set up the satellite into the stable orbit. Okay. And once the satellite is placed in the stable orbit, then by some mechanism it is given a necessary orbiting velocity which is actually called insertion velocity, and it is denoted by Vi. And after giving this necessary velocity to the satellite in that orbit, it revolves around the Earth. Okay. You can see in this figure I have shown here that this round body is actually your Earth. This is Earth, and its center is at O and its radius is R. And at a height h from the surface of the Earth, there is a point P where the artificial satellite has been placed by the help of the multi-stage rocket at this point P. It means the orbit of the satellite uh, is at a height h from the surface of the earth, and here by some mechanism it is provided a velocity vi, which I have shown in this figure. This is called insertion velocity. This is the velocity required for orbiting the satellite about the sun. Okay. As you know, you have studied while discussing the trajectory of a particle moving in a central force field, that depending upon this velocity or the total energy of the satellite, the orbit of the satellite may be elliptical, it may be a hyperbola, it may be a parabola, or even it may be a circle. Okay. It all depends what is the total energy of the satellite, or what is its insertion velocity. That decides the nature of the orbit. Okay. So if you want to find the insertion velocity required for revolving the satellite around the earth, first of all you have to find what insertion velocity will be needed for it. And for this we will actually find what will be the total energy of the satellite revolving in an orbit which is at a height, let us say h, or the point of projection p, which is at a height h, with which velocity the satellite is projected. We have to find it. So now let us try to find what will be the total energy of the satellite when it was at a point P, which is at a height h from the surface of the earth. Now you can see, if this capital R is the radius of the earth, then from the center of the earth, the distance of point P from where the satellite will be projected, that will be R plus h. That will be R plus h. So you have to find the total energy of this satellite when it is located at a distance R plus h from the center of the earth. Okay. When you say total energy, that means kinetic energy and potential energy of the satellite. Okay. If you consider that Vi is the velocity with which the satellite is projected, then its kinetic energy will be what? That will be half mvi square. This is kinetic energy of the satellite. Okay. Here we consider that this earth is a stationary. We consider it because it is very massive in comparison to the satellite, and so that in this interaction we assume that the earth is not in motion, only the satellite is in motion. And this is not very wrong, because we consider that mass of the earth, which is denoted by the symbol capital M, this is much greater than mass of the satellite small m. So in this, if this condition holds, then we can assume that during this interaction between the planet, between the earth and the satellite, the earth remains stationary. We can assume it. Okay. So earth has no kinetic energy. This kinetic energy totally of the kinetic energy of satellite. And apart from this, there will be a gravitational interaction between the earth and this satellite of mass small m. So there will be gravitational potential energy in this system. And you know, since earth is spherical and the satellite is situated at a point which is outside of the surface of the earth, so in this condition we can treat that the total mass of the earth is concentrated at its center. For calculation we can assume it. So the problem is, for calculation of potential energy like this, you can assume that there is a mass capital M which is equal to mass of the earth, and there is another mass which is a small m, which is mass of the satellite, and the distance between these two is R plus h. r plus h. Okay. Now for calculating the potential energy, we must have to take under account the reference point or reference level. Here, for simplicity, we consider the reference for the calculation of gravitational potential energy at the center of the earth. It means at the center of the earth we consider that gravitational potential energy is zero. So in this condition that gravitational potential energy of this earth plus satellite system will be what? That will be minus g mm divided by r plus h. This is a well-known formula. Okay. So this is the total energy of the earth plus satellite system. Okay. Equal to this much. Here this g is universal gravitational constant, and capital M is mass of the earth and a small m is mass of the satellite. Okay. So actually I have made this calculation. You can see it here that a satellite of mass m is projected horizontally with velocity vi from a point P at a height h from the earth's surface. And we have assumed that capital M is mass of the earth, r is radius of the earth. Then the total energy of the satellite at point P, taking the center of the earth as a reference to measure the gravitational potential energy E, will be equal to what? E is sum of kinetic and potential energy, and we have seen that kinetic energy is half mvi square, and potential energy, that is gravitational potential energy, will be minus gmm divided by r plus h. This is the expression for the total energy of the satellite at the point of projection. Okay. Now this total energy may be positive, it may be zero, it may be negative. All possibility are here. So if you consider that the total energy E of the satellite is greater than zero, that is positive, then what will happen? As you have studied earlier, that eccentricity of the trajectory depends on the value of the energy and the angular momentum of the particle in a central force field. Here I have written this expression which we have learnt in the previous lectures, that eccentricity of the orbit or trajectory is given by 1 plus 2 ej square divided by mc square to the power half. Here actually this c is equal to gmm, gmm. This is for c. And you can see that in this second term, except E, all quantities are positive. J square will be positive, m is positive, c square is positive. So the sign of this term 2ej square by mc square will completely depend on the sign of E. Okay. And so when you consider that E is greater than 0, it means positive, then from this relation for eccentricity E, you can see that eccentricity will be then greater than 1, because this 2ej square by mc square will be a number which will be positive, and that will be added in 1, so there will be a number greater than 1. Okay. So eccentricity will be then greater than 1. And you know from coordinate geometry that if eccentricity of a conic or a trajectory is greater than 1, that conic or that orbit or that trajectory will be hyperbola. So in this condition, if energy of this system is greater than 0, then you can say that our satellite will follow a hyperbolic orbit. I have shown in this figure. You can see that this is a hyperbolic orbit, and I have mentioned it here that this trajectory will be followed by the satellite when its total energy is greater than 0, or the eccentricity of the orbit is greater than 1. Okay. But if you consider that the total energy E is equal to 0, it means the kinetic energy is equal to the magnitude of the gravitational potential energy, then E will be 0. In this condition, you can see from this formula for eccentricity that if E is 0, eccentricity will be simply 1. And in this condition, the orbit is a parabola. And you can see, I have shown here that this path is represents a parabola, and it will be possible when the total energy of the system is 0, or the eccentricity of that trajectory or conic is equal to 1. Okay. But if you consider that the total energy of this satellite is less than 0, okay, less than 0, it means negative, then see this expression for eccentricity. Eccentricity, when E will be negative, then eccentricity will be less than 1. And if eccentricity is less than 1, then you know the orbit is an ellipse. So in that condition, you can see, I have shown here that when E is less than 1, small e, or capital E is less than 0, in that condition our satellite will follow an elliptical path. Actually, in practice, when we project a satellite in an stable orbit, the velocity has such a particular value so that it revolves in this elliptical orbit, okay, or in circular orbit. So these two options are followed in practice. It means we avoid the hyperbolic path and the parabolic path. In practice, the satellite are provided such a velocity so that its path will be either a circle or an ellipse. So you can see, if the eccentricity will be equal to 0, eccentricity will be equal to 0. When its eccentricity will be 0, it means when this 2ej square over mc square, this will be equal to -1. In that condition, eccentricity will be 0, and for that particular value of energy, the orbit will be circle. Okay. So we will discuss further only the elliptical orbit of the satellite and the circular orbit. Okay. Hyperbolic orbit or parabolic orbit are not of practical interest. Okay. Although it may be possible, but it is not in practice. So now we consider a satellite moving in an elliptical orbit. Okay. And as you have seen, if the satellite is revolving in an elliptical orbit, then its energy is less than 0, that is negative. And you have seen that total energy is what? This is this much. This is half mvi square minus gmm by r plus h, and this will be less than 0. And if it is less than 0, that is negative, what does it mean? It means half mvi square is smaller than gmm by r plus h. M will actually taken as a common factor, and that will be removed. So you can say that vi square by 2 will be less than gm by r plus h. And so vi will be smaller than a square root of 2 gm by r plus h. So you can see, if the satellite is provided an insertion velocity vi which is smaller than this value 2 gm, a square root of 2 gm by r plus h, then that satellite will follow an elliptic orbit. Okay. So if the satellite is aimed to revolve around the earth in an elliptic orbit, the velocity of the satellite is limited. Its value must be smaller than this value root over 2 gm by r plus h. And you can see, actually this value of velocity depends on the height of the satellite from the surface of the earth. So h limits what will be h, for a particular h, a particular value of insertion velocity will be required. Okay. So when the orbit will be elliptical, you can see this condition has been expressed here in terms of insertion velocity. For elliptic orbit or a satellite, you can say revolves around the Earth along an elliptic orbit only when the insertion velocity provided to the satellite is smaller than a square root of 2 gm by r plus h. Okay. Now, we will talk about a circular orbit. Now, let us consider that satellite is provided a velocity so that it moves in a circular orbit. This is a circle, you can see. And in this condition, for circular motion, the object must require a centripetal force. Here, at this point P, there is satellite which has been projected by velocity vi, okay? And this is your Earth whose mass is capital M. And you know that this Earth attracts the satellite towards its center by exerting a gravitational force F. And if the satellite will move along this circular orbit whose radius will be actually equal to r plus h. A small r, this represents the radius of the circular orbit, and you can see the figure. This radius of the circular orbit will be r plus h, where capital R is the radius of the Earth, h is height of the circular orbit from the surface of the Earth. Okay. And for circular motion, a centripetal force is required. Centripetal force provides the circular motion. Here, the gravitational force exerted by the Earth on the satellite acts as a centripetal force. And due to that very force, the satellite revolves along this circular orbit. So if you will write the equation of motion of this satellite, what will be that? The equation of motion is written as F equal to ma. But here in circular motion, this acceleration is equal to v square by r, which is called centripetal acceleration. And this F, what is this F? F is the gravitational force exerted by the Earth on the satellite. And this force will be what? From Newton's law of gravitation, this force will be gmm by r plus h whole square. And that will be equal to mvi square over r plus h. Here, actually, v has been assumed vi, which is insertion velocity. Now, one of this r plus h will cancel out in both sides, and from here you can see this small m is also a common factor, so this will be also cancel out, and this vi will be equal to gm divided by r plus h square. This is the insertion velocity required for the circular motion of our satellite around the sun. This is also called orbital velocity. This velocity is also known as orbital velocity. Okay, you can also call it orbital velocity or insertion velocity. Okay, so if the satellite will provided this much velocity, which has been defined in equation 3, then its orbit will be circular. Okay. Now we will see what will be the time taken by this satellite revolving around this circular orbit once during its motion. Okay. And the time taken by this satellite in one revolution is called time period of this motion or period of revolution. And what will be that? That is a very simple calculation. As you can see, the radius of this orbit is small r, which is equal to capital R plus h. So in one revolution, what will be the distance covered by the satellite? That will be simply equal to the circumference of this orbit, and that will be 2 pi r. This is the distance covered by the satellite in one revolution. And this distance is described by the satellite with a constant speed vi. So when you will divide the distance covered by the satellite by its speed, you will get the time period. Sorry, this is not s. S is 2 pi r. But if you want to find the period of revolution, what will be that? If we denote it by t, then this will be distance covered in one revolution, which is 2 pi r, and divided by a speed with which this distance has been described. So t will be 2 pi r divided by vi, but a small r is equal to capital R plus h, so that this period will be 2 pi times r plus h divided by vi. Okay? And in circular motion, you know, or in case of circular orbit, vi is this much. So we'll substitute these values and you can see that t will be equal to 2 pi times r plus h divided by vi. Okay? But vi, as you have seen, that vi is equal to this much, and when you will substitute this value of vi here, your result will be 2 pi times r plus h times r plus h whole to the power half divided by square root of gm. Okay? And so t will be simply 2 pi times r plus h whole to the power 3 by 2 times, divided by root over gm. This is actually the expression for the period of revolution of this satellite if it is revolving in a circular orbit. Mark it. This is time period for circular orbit. Okay? Now let us consider that our satellite is revolving in a circular orbit which is very close to the surface of the earth. Very close. As you can see that the radius of the orbit is r plus h, but you are assuming that satellite's orbit is very close to the surface of the earth. It means this h is very small. When you say very small, anything is smaller in comparison to another thing. Here h is very small means h is much smaller than r. That is, height of the orbit of the satellite is much smaller than the radius of the earth. You know, radius of the earth is almost 6400 kilometer, and if your satellite is revolving like 100 meter above the surface of the earth, 200 meters above the surface of the earth, that 100 meter and 200 meter will be just neglected in comparison to the radius of the earth. So in this condition, this r plus h will be almost equal to r, because h will be neglected in comparison to this capital R. And so that you can write in this very condition for a satellite which is revolving around the earth in an orbit which is very close to the surface of the earth, the time period or the period of revolution will be what? We will simply neglect this h. So this will be 2 pi times r to the power 3 by 2 over root gm. Over root gm. Now, this root over gm can be found like this. Let us see if this is your earth having radius r, okay, and on the surface of the earth there is a mass m, or you can imagine that if the satellite is exactly on the surface of the earth, then the earth will attract it by a force F, and you know the force of attraction by the earth on a body is simply the weight of the body. So if acceleration due to gravity at the surface of the earth is small g, then you know weight will be what? Weight will be m into g, mass times acceleration due to gravity. Here g is the acceleration due to gravity on the surface of the earth. That is equal to the force of gravity. This is just definition of weight. So mg will be simply equal to gmm by r square. Here separation between this small m and the capital M is small capital R. And so from here you can see that this m and m will cancel out, and you can see that acceleration due to gravity at the surface of the earth is simply gm divided by r square. And so you can see this gr square will be equal to gm. Hence, in this expression, at the place of this gm, now you can write this gr square, where g is acceleration due to gravity at the surface of the earth. So the period of revolution in this condition can be written as t equal to 2 pi times r to the power 3 by 2 divided by root over gr square. Okay, and this will be 2 pi r to the power 3 by 2 times divided by root over g times r. Now this r will cancel out, and when this r will cancel out in the numerator, there will be r to the power half. So your result for t will be 2 pi root over r by g. Now you can see r is almost 6400 kilometer. Okay, so in meter you can write the value of r as 6.4 into 10 to the power 6 meter, and we assume that g is almost equal to 10 meter per second square. When you will simplify it, you will get that t is equal to 2 pi times 800 second. And when you will divide it by 60, the result will be 84.6 minutes, which is almost equal to 1.4 hour. So the period of revolution of a satellite which is revolving in a circular orbit which lies very close to the surface of the earth, the period of revolution is fixed and it is equal to 84.6 minutes, almost 84.6 minutes. Okay, this is actually a very well known result. This formula which I have mentioned here, this is a very important formula, because you can see there are several situations when you will see that time period is like this, 2 pi root over r by g. This is a well known result. I have mentioned here three situations. Along with that situation, there are three more situations in physics where you find that time period is same, that is 84.6 minutes. In first example, I have mentioned that if you consider a simple pendulum whose length is equal to infinity, if length of a simple pendulum is infinity, then its time period is 2 pi root over r by g. I have actually provided a video on this. You can see a video that when L is infinity, then time period is not infinity of a simple pendulum, but it is 2 pi root over r by g, which will be 84.6 minutes. Okay, actually the formula t equal to 2 pi root over L by g is not valid for a simple pendulum whose length is infinitely long. Okay, but formula changes. If L tends to infinity, t is equal to 2 pi root over r by g. So this situation that there is a simple pendulum of infinite length, we get the same time period as the time period of a satellite revolving in a circular orbit very close to the surface of the earth. In both cases, time period is same, and that is 84.6 minutes. And another important example for the same time period you will see in the chapter gravitation, when you discuss that if you make a, let us say, a tunnel through the center of the earth, okay, this is center of the earth, and you make a tunnel through the center, and you drop a particle from one end of the tunnel, it will move toward the center of the earth, and then again it will reach to the another side of the tunnel. But this particle will execute a simple harmonic motion in this tunnel about the center of the earth. Okay, it is not necessary that the tunnel should be through the center of the earth. Tunnel may not be through the center of the earth, it may be uh, uh, through another position. For example, you can see this figure there. This is the center of the earth, but I have made a tunnel here, and when the particle will be released from one end of the tunnel, again it will make a simple harmonic motion along the center of this tunnel, not the center of the earth. And in both of the situations, time period of this simple harmonic motion will be 2 pi root over r by g. Okay, in this condition too. Now, the third situation, I have mentioned it here, that if you consider that earth is rotating with such an angular velocity so that at the equator everybody becomes weightless. It means if you say that g, acceleration due to gravity at the equator, which I have denoted by ge, is equal to 0. If g becomes 0 at equator, in that condition omega of the earth, that is angular velocity of the earth, is such that the time period will be equal to 2 pi root over r by g. It means in that condition the angular velocity of the earth becomes root over g by r. Then time period will be what? Time period will be 2 pi root over r by g. It means time period of earth rotation will be also equal to 84.6 minute. But when its speed becomes such that the acceleration due to gravity at the equator becomes 0. So these are the 4 situations when time period is same. First situation we have discussed here. There is a satellite revolving very close to the surface of the earth in a circular orbit. The time period of such a satellite is 84.6 minutes. In another example, you have seen that if there is a simple pendulum whose length is infinity, the time period of such a simple pendulum is also 84.6 minutes. Okay? The time period of a simple harmonic motion of a particle or a body or a male through a tunnel in the earth is also 84.6 minutes. And the time period of earth rotation is also 84.6 minutes when its speed becomes such that the weight of a body at the equator becomes 0, or the speed becomes such that the speed of the earth becomes such that acceleration due to gravity at the equator becomes 0. In all these 4 situations, time periods are same, and the well-known formula for that time period is what? This is t equal to 2 pi root over r by g. Okay? Actually, when you write an answer of such a question for artificial satellite particularly in civil services examination, if your optional is physics, then definitely after writing or finishing the answer, you must compare your final result with the other situations where you get the same result. So if you are writing this answer for civil services examination, you must mention all these 3 remarkable facts. Then you will get good marks. In university examination, it is not very essential, but in competitive examinations, this comparison is very essential. Then you will be awarded good marks. Okay. So I think you have definitely learnt about this artificial satellite. In continuation of this lecture, in the forthcoming lecture, again we will see the artificial satellite, particularly geostationary satellite. Okay, and hope you will watch this video seriously, enjoy it, and definitely you will be benefited. It is my keen faith. Okay, thank you very much.